Okay, hello everyone. Today we will learn Chapter 11, Linear Models and Estimation by Least Square, Part 3. Previously, we used this term to estimate population variance sigma square. In this case, the assumption is that y1 to yn follows some distribution, IID distribution, and expected value of y is 0 and variance of y is sigma square. And in this case, to estimate sigma square, we used this estimator. And now the situation is like this: yi equals beta 0 plus beta 1 xi and plus epsilon. And in this case, we assume that expected value of epsilon is 0 and variance of epsilon is sigma square. And so, and also yi hat is beta 0 hat plus beta 1 hat times xi. So it it would be natural that to estimate the variance of epsilon, we use the yi minus yi hat. Sum of this term I equals 1 to n. And so it is natural that we are using this term to estimate sigma square. And actually, we can prove that expected value of s square, and if we define our s square this way, this is 1 over n minus 2 and with this term, and then this we can show that this is sigma square. So let's move on to prove that this one holds. Let's prove the expected value of s square is equal to sigma square, where s square is this thing and SSE can also written as this thing, and where SYY is defined this way. And similarly, in the previous calculation, we know that SX is this is definition that I use in the proof for the simplicity. Sxy is integration sum of xi minus x bar yi minus y bar. Okay, this is the term that I will use inside of the proof, and let's try to prove this one. Expected value of s square can be written as expected value of 1 over n minus 2 times SSE, and 1 over n minus 2 is constant, so expectation goes inside to here. And so let's try to find what is expected value of SSE, and that is expected value of sum of yi minus yi hat. And this is because yi is beta 0 plus beta 1 xi plus epsilon I, and so and also yi hat is beta 0 hat plus beta 1 hat xi. So remember this, we have this one, and so we can put yi hat this one, and then this becomes sum of yi minus beta 0 hat minus beta 1 hat xi squared. We have squared here. And now let's use the one that we previously solved. Beta 0 hat is y bar minus y bar minus beta 1 hat x bar. Okay, and what was beta 1 hat? Beta 1 hat was beta 1 hat was sxy sxy divided by sxx. Okay, so we previously showed this one, and let's put beta 0 hat here. Okay, then this one becomes expected value of sum of yi minus y bar plus beta 1 hat x bar, that's this one, and minus beta 1 hat xi squared. And we can rewrite this one as the expected value of sum of yi minus y bar minus beta 1 hat xi minus x bar, okay, squared. Okay, and now we can re-express this one as the expected value of sum of yi minus y bar squared minus 2 times beta 1 hat sum of yi minus y bar xi minus x bar plus beta 1 hat squared sum of xi minus x bar squared. Okay. Now we know that this thing. So from here we know that beta 1 hat sxx is sxy. So in this notation, this part beta 1 sxx, this is sxx, and this is sxy. So beta 1 sxx is sxy, so this one can be written as plus beta 1 hat sxy, and this part can be written as minus 2 beta 1 sxy. So the inside part can become this part is syy and minus beta 1 hat sxy. So here we showed that SSE can be written as this way. But to prove this thing, it is easier to write it this way. Actually, this is SYY. We can also write this way. SXY is beta 1 SXX, so we can write it as minus beta 1 square SXX. Okay, so we can write it this way, and let's try to solve this one from the next slide. Okay, from this notation, actually SYY, the sum of yi minus y bar squared, and actually this part can be written as sum of yi squared and minus 2 times sum of yi y bar minus n y bar squared. And actually this one, sum of yi is n times y bar, and so this part is plus, and so this one becomes sum of yi squared minus ny bar squared. So this, because of this thing, this notation can be rewritten as sum of yi squared minus ny bar squared minus beta 1 squared sxx. Okay, and that thing becomes sum of expected value of yi square minus n times expected value of y bar squared and minus expected value of beta 1 squared times sxx. And so let's put, and what we know is variance of yi square, variance of yi is expected value of yi square minus ey square. So EYI square is variance of yi plus ey square. So this one becomes variance of yi plus expected value of yi square minus n times variance of y bar plus expected value of y bar squared and minus this is variance of beta 1 hat plus expected value of beta 1 hat squared times sxx times sxx. Okay, and so this one becomes sum of variance of yi is sigma square. So this is sigma square and plus expected value of yi. It is actually beta 0 plus beta 1 xi plus epsilon, and expected value of epsilon is 0. So yeah, this one squared, this one squared minus n times variance of y bar is n over sigma square and plus expected value of y bar is beta 0 plus beta 1 x bar squared and minus variance of so sxx times variance of beta 1 hat is sxx sigma square over sxx from the previous calculation, and expected value of beta 1 hat is beta 1. So beta 1, that is expected value of this thing, and this one squared. So this is what I get, and from here from the this is n times sigma square plus sum of beta 0 plus beta 1 xi square and minus sigma square minus n times beta 0 plus beta 1 x bar square and minus sigma square minus sxx beta 1 square. Okay, and from here we have n minus 2 sigma square and what else? Let's rewrite this part. So this part is beta 0 square plus 2 times beta 1 beta 0 xi plus xi square. Sum of this thing plus minus n times beta 0 plus beta 0 beta 1 x bar 2 times and plus beta 1 square x bar square and minus sxx beta 1 square. Okay, and from here we can check that this part, summation with this part and this part and cancelled out because sum of xi is n times x bar, and so these red parts can be cancelled out. And what about this part? What about so this red part first cancelled out, and sum of xi square minus oh, here we have beta 1 square, beta 1 squared, and n times beta 1 squared x bar squared. And actually this thing is beta 1 squared sum of xi minus x bar squared. If you rewrite this thing, then you can prove that these are equivalent. And actually this is beta 1 square sxx. And so this beta 1 square sx part and beta 1 square sx part cancelled. So only this part remains. So this is the proof that expected value of s square expected value. So this is proof for the expected value of SSE is n minus 2 times sigma square. So expected value of S square is sigma square. So you can prove that. Okay, let's move on to example 11.3. Estimate sigma square from the data given in example 11.1. So to estimate sigma square, the one good estimator would be S square because expected value of S square is sigma square. So we were going to use S square to estimate sigma square, and to calculate S square, we can use this calculation. So from the data we can use R. So to store the data, let's define xi as minus 2 to 2, and let's define yi as 0, 0, 1, 1, 3. And after this defining stage, and we can calculate sxx, sxx, sxy, syy. And actually in the calculation we only need syy and sxy, but in the calculation of beta 1 hat, the beta 1 hat, we need to calculate it with sxy divided by sxx. So we need to calculate everything. To do that, this is sum of xi minus x bar squared. So to calculate that, we will write it this way in our R code, and from these calculations we can check that our sxx is 10, our syy is 6, and our sxy is 7, and our beta 1 is 0.7. And after calculate all these numbers, now we are ready to calculate our S square. We can calculate SSE by this definition using this code, and also we can calculate S square by dividing SSE to n minus 2, which is 0.3666. Yeah, this thing. Okay. Uh, You can solve this problem using matrix form as well. So previously I solved the similar questions using matrix forms as well. So I'd like to also explain this with matrix form. So SSE, it is sum of yi minus yi hat squared. And actually, if you write this again with matrices, you can write it this way: y1 minus y1 hat, comma dot dot dot, yn minus yn hat, and let's say this is matrix y1 minus y1 hat dot 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 yn minus yn hat. So let's say this vector is y minus y hat. If we define this vector this way, then this sum of this one can be written as y minus y hat transpose y minus y hat. Okay, so we can calculate SSE this way, and also here y hat is x transpose x inverse x transpose y. So your no, this is beta hat. Wait a minute, beta hat, and y hat is beta hat x. So yeah, so you can calculate this one using matrix form. So here is the calculation. Your matrix X can be described this way. So your X is something like this. And your Y is 0, 0, 1, 1, 3. And you can solve your beta hat from here. And this part is Y minus X beta hat. Transpose y minus x beta hat, and so the result divide by 5 minus 2, and the result is the same, 0.36666, and so you can calculate estimate of sigma square this way as well. So this is the summary slide for what we've learned in this chapter. The first one is we learned that both beta 0 hat and beta 1 hat are unbiased. So this means expected value of beta I hat is equal to beta I. And we also showed what is variance of beta 0 hat and what is variance of beta 1 hat, and we also see what is covariance of beta 0 hat and beta 1 hat. And we also covered the general case when beta hat is x transpose x inverse x transpose y. For the general case, we also showed it is unbiased, and variance and covariance. We showed all of that, and we showed this one as well, and we didn't show this one yet, but so far we assume that epsilon I are IID distribution, and expected value of epsilon is 0, variance of epsilon is sigma square. And if we additionally assume that this epsilon I are normally distributed, then the following things are hold. Both beta 0 hat and beta 1 hat are normally distributed, and several other things. I didn't prove it yet, but I'm not. I don't sure whether I will prove them or not. But these knowledges will be covered in linear regression or linear model class, I believe. So maybe I will skip, or I don't know whether I will cover it yet. But anyway, it would be good to know if epsilon I is normally distributed, then you can proceed the following reasonings as well. Okay. And here is homework for 11.4. Okay, let's move on to chapter 11.5, inferences concerning the parameters beta I. Suppose we fit the model of something like this. Then if we wish it to test, the null hypothesis is beta 1 is 0 and alternative is beta 1 is not 0. Then what would be the test statistic and how we can do the test related to this? This is the thing that we want to cover in this chapter. And so actually to do these type of inferences, we need additional assumptions. So we have estimate for beta, which is beta hat. But we don't know the distribution of beta hat. However, if we know that the epsilon part, this part follows normal distribution with mean zero and variance sigma square, then we can show that beta I hat is unbiased and normally distributed. We proved that beta I is unbiased, and so the additional thing to prove is beta I is normally distributed. And it's easy to prove that beta 0 hat and beta 1 hat, they are linear combination of yi's. If epsilon follows normal distribution with mean zero sigma square, then y follows normal distribution with mean beta 0 plus beta 1 x and variance sigma square. So the y variable yi also follows normal distribution, and we can show that beta 0 and beta 1 are linear combination of yi's. And so the distribution of beta 0 and beta 1 hat, it is also normal distribution with mean something, variance something. So if this assumption holds, we can show that beta I is unbiased and normally distributed. And also, we calculated the variance of beta I hat. So the variance of beta 0 hat and variance of beta 1 hat, we showed this thing. So now we know the distribution of beta hat. So and with the matrix notification, it's more easier for the general case. Beta hat is x transpose x inverse x transpose y, and variance of beta hat is x transpose x inverse sigma square. So beta hat, distribution of beta hat, it is normally distributed. And here we can check that this is this is matrix, and this is linear combination of y. So beta hat is again normally distributed with mean beta. So if you calculate expected value of beta hat, it is since y is x beta, the expected value of beta hat becomes beta. So beta and variance of x transpose x inverse sigma square. And so this is the distribution of beta hat. And this is same as this one. This is, yeah, so, okay. So to test the hypothesis beta I is equal to beta I 0, we can use the test statistic. So we can use the, so beta hat follows normal distribution with mean beta and variance x transpose x inverse sigma square in matrix form. This or we also know the beta 0 follows normal, beta 1 follows normal. So we can use distributional knowledge to construct the test statistic, which is our z statistic. And so this is the test statistic we derived. And for the small number of samples, like if we have less than 30, then we can use the t-test, which is so replace sigma with s, and we can define our t-statistic this way. Okay. Here is the summary slide how you do the hypothesis test for beta I. For a given hypothesis testing, you can construct your t-test statistic this way, and you can construct rejection region this way, and also yeah, how you proceed the test. Anyway, if the sample size is sufficiently large, you can replace this as G. You can use the normal approximation if n is sufficiently large. But if your n is small, like smaller than 30 or something, then you can use t-statistic like this. Let's move on to solve some exercise problems, example problems. Let's move on to example 11.4. Do the data of example 11.1 present sufficient evidence to indicate that the slope difference from 0? So slope is beta 1. We want to test beta 1 is whether 0 or not. Test using alpha equals 0.05 and give bound for the attained significance level. So let's specify the test statistic first. Our null hypothesis is beta 1 is 0 versus beta 1 is not 0, and our alpha is 0.05. And this is our step 1, and the step 2 is the hypothesis, test statistic. And test statistic would be related to beta 1, and the beta 1 hat follows when the sample size is large, then it would follow normal distribution. No, actually, it doesn't depend on the normal sample size. Beta 1 hat follows normal distribution with beta 1 and the variance component. And from the previous slide, we derived that the variance component is this thing, and this thing will follow the normal distribution. However, since we only have 5 samples, we will use t-distribution and replace this sigma with s divided by ci, and beta 1 hat minus 0. So we will use this t-statistic for our test. And what would be the next? The next thing is to calculate the test statistic. Let's see. So here's the data, and here's actually I think that you are familiar with this example. I did it a lot, and so here's the part that I calculate our t statistic. T is b1 minus 0 divided by s square root of s2 divided by sxx, which is the variance of beta 1 hat. And we get the number 3.65556 something. Okay, and the next thing is the decide rejection region, which is for two-tailed case. The rejection region is if our absolute value of t is greater than t alpha over 2. And what is t alpha over 2? We can calculate it using r, and that value is 3.18. And actually 3.18 3.6556 is greater than 3.18. So our conclusion is reject the null hypothesis. Reject null hypothesis with alpha level 0.05. We can also calculate our p-value. So this is the t-distribution, and our test statistic is 3.6556, and the area, this part and this part, this one is minus 3.6656. If sum of these two values, that's the p-value. So to calculate p-value, it is 1 minus p 3. Or actually 655 or something. Maybe this is 6. No, you can do it this way, but the solution should be very similar to this one. So it is 2 times 1 minus pt 3.6556. Then this thing is the area here. We need 2 area here, so we multiply 2 times this thing, so this is our p-value. So p-value is 0.035, or maybe slightly different from this one, since I do some mistake. Anyway, you can do calculation this way. The next problem is how we can calculate the confidence interval for beta I. Actually, it is very similar. Since we know the distribution of beta I hat, we can construct 100 times 1 minus alpha % confidence interval using this formula. Let's try this formula with example 11.5, which is the previous problem. Calculate 95% confidence interval for the parameter beta 1 of example 11.4. Actually, to do this, we do the same calculation that we done in the previous problem, and also it is just plug in the values. And so if we calculate beta 1 hat minus this qt part is t alpha over 2, and this part is square root of s square divided by sxx, which is variance of beta 1 hat, and so the calculation is this thing. So the confidence interval, 95% confidence interval for beta 1 is 0.0906 and 1.309 309 or something. Okay, so this is 95% confidence interval for parameter beta 1. Let's try to solve the exercise problem 11.26. Most sophomore physics students are required to conduct an experiment verifying Hooke's law. Hooke's law states that when a force is applied to a body that is long in comparison to its cross-sectional area, the change y in its length is proportional to the force x, that is this. So this one is Hooke's law, and where beta 1 is a component of proportionality, the result of a physics student lab experiment are shown in the following table. 6 lengths of steel wire 0.34 millimeter in diameter and 2 meter long were used to obtain the 6 force length change measurements. Okay, so here's the data. The force is x and change in length is y. So and this is Hooke's law. And let's try to prove number A to E. A is fit the model y equals beta 0 plus beta 1x plus epsilon to the data using the method of least squares. And I mentioned that there's two ways, the general proof or the simple regression specific proofs. And in previous example, I used specific simple regression proof. So this time I would like to go with matrix form. So I tried to estimate beta hat with this one, x prime, x transpose x inverse, x transpose y. So this is our beta hat estimate, and using method of least square, and these are our estimates for beta 0 hat, and this is for beta 1 hat. Okay, and let's move on to number B. Find a 95% confidence interval for the slope of the line. In the previous example question, I did it using the specific simple regression way. So this time I solved it using matrix notation. So the S square is transpose of y minus x beta hat transpose y minus x beta hat divide by n minus 2. This is S square estimate using matrix form. And for the variance of beta hat, this is x transpose x inverse sigma square, and if we put our estimate here, which is S square, this is our variance estimate component. X transpose x inverse, x transpose x inverse is this part, and times S square, which is this one. So in this matrix, this part is variance of beta 0 hat, and this part is variance of beta 1 hat. Okay, and in number B, we want to find 95% confidence interval for the slope, which is beta 1 hat. And so beta 1 hat is this thing from the beta hat 2 is beta 1 hat. So beta hat 2 plus minus this thing is 95% confidence interval. So here we have Qt, and here's the square root of variance of beta hat, beta 1 hat. Okay, so from here we can see that the confidence interval is this one. For beta 1, it is 0.1100, 0.11, 0.1, 0.126, 0.110. Okay, so this is our confidence interval for the slope parameter. And let's move on to number C. According to Hooke's law, the line should pass through the point 0.0. That is, beta 0 should equal to 0. Test the hypothesis that expected value of y equals 0 when x is 0. So what we are testing is that the hypothesis, null hypothesis, is beta 0 is 0 versus h1 beta 0 is not 0. And we didn't specify the significance level for this, but in E we specify alpha equals 0.05. So let's try to set our alpha as 0.05. And to test about beta 0, let's calculate. Actually, we already have all the numbers related to beta 0 because here we have distribution for beta hat, which is normal, mean beta, and variance of beta hat, which is x transpose x inverse sigma square s, actually square. Anyway, this is our estimate for beta hat, so we can construct a test for this. And so our t-test is like this. Our t-test is beta 0 minus 0 and divide by square root of variance of beta 0 hat. Okay, so this is our t-test statistic, and which is 4.587. And okay, so this is our t statistic, and also you can calculate qt something like this for this case as well, but I didn't do it here. Rather than that, I calculated the exact p-value. So if you calculated the t-statistic, you can calculate the exact p-value, which is so here's 4.587, and so p-value is for the two-sided test. If you sum up these two probabilities, that's the p-value, which is this thing, and your p-value is 0.0101. So the p-value is this thing. And what would you conclude that alpha equals 0.05 level? Since your p-value is less than 0.05, you will reject the null hypothesis. So reject the null hypothesis. And so we support that beta 0 is not equal to 0. This is our conclusion, and yeah, okay. Here are homework for chapter 11.5.